Right, good morning Year 9. So today we're looking at giant covalent structures. So last lesson you looked at covalent bonding, which is the type of bonding that happens between non-metals. You learned that electrons are shared and that the covalent bond itself, the overlap, is very, very strong. So just like giant ionic bonds that can add together to form giant structures, we can also get giant structures with covalent bonds as well. So just to recap some of the properties of giant ionic, they have high melting points and boiling points because they have lots of electrostatic attraction, which is strong, so needs lots of energy to overcome. They can conduct electricity when molten or dissolved because the ions are free to move and carry charge, and they're solids at room temperature because they have high melting points and boiling points. So generally speaking, for giant covalent, these are the general rules for every single one apart from graphite, which we're going to look at separately. So these are our general rules. So if you ever get something that's giant covalent, these are the rules for it. So they also have high melting points and boiling points. The reason for that, they have lots of covalent bonds which are strong and need lots of energy to overcome. So an almost identical statement, just change those two words there. Because remember, ions, we've got positives and negatives, so it's electrostatic, that means opposite charge attraction. These are covalent bonds. They do not conduct electricity because they don't have any free electrons or ions to move and carry the charge. They are also solids at room temperature because they also have high melting points and boiling points. So for us to understand giant structures, we need to understand how these can build up to start with. So I've got two hydrogens here, each one needs one, each one will share one to form our covalent molecule. Our covalent molecule is held together by a strong covalent bond. Now if another covalent molecule comes nearby, like this one here, they have this sort of force of attraction. They're called intermolecular forces. It literally translates as forces between the molecules. So although neither of these are charged, if they come near each other, so if this hydrogen molecule here comes near another hydrogen molecule, we get these intermolecular forces. These are really weak. They're really easy to break. Most of them are gases at room temperature because that's enough energy for this hydrogen molecule to move away. So strong covalent bonds, and then in between each one we have these weak intermolecular forces. Okay. So looking a bit more specifically then at diamond. So we're going to look at two examples. We're going to look at diamond and we're going to look at graphite. The reason we look at them in specifics is because they're both very different even though they're both made of carbon. So diamond, each carbon bonds to 4 other carbons. As we know, carbon is in group 4 of the periodic table. That means it has 4 outer shell electrons. It wants to bond with 4 other things. So each carbon bonds to 4 other carbons. This means it has a full outer shell of electrons. It builds into something called a tetrahedral shape. So it kind of, if I say diamond, you can all picture what I mean by the shape. That's a tetrahedral shape. I can't draw. My class know this. Anyone that's been taught by me in Year 8 knows this. I can't draw. So have a quick look at a picture. You are not expected to be able to draw it, but if you see it, you'll understand what it means. You'll recognise it and know it's diamond. So just have a quick look at a tetrahedral shape or just type in structure of diamond and it will come up. So you need to understand the properties and then be able to explain them. It's the same for graphite. So I've picked the same 3 comparative properties so you can easily learn the statements. So diamond is strong or hard. We know that it's the sort of hardest non-man-made substance. So it's strong or hard, and the reason for that is because there's no layers to slide over each other. So if you imagine your hands, that's one layer, that's another, you can move them about. If you think when you're cold you do that, so we've got our layers and they can move about. Whereas in diamond we don't have any layers, so the layers can't slide over each other, so it means that it's really strong. Has a high melting point and boiling point because it's got lots of strong covalent bonds which require lots of energy to overcome. The final thing is that it doesn't conduct electricity. The reason for that is there's no free or delocalized electrons that can move and carry charge. These words here are the same thing. In an exam you only have to write one of them. I tend to teach it as free electrons, but some people teach it as delocalized electrons. Both are correct. So I've put both words in there so you're not puzzled next year when someone starts talking about the other one. So no free or delocalised electrons that can carry charge. So to summarise, diamond is a pretty generic giant covalent molecule. It has a high melting point and boiling point. It is strong, it's hard, it doesn't conduct electricity, and it's a tetrahedral shape. So we're going to look at graphite. Graphite is an absolute exception to the covalent rule. So graphite, we still have carbon. So this is why diamond and graphite are quite often used, because they're both giant covalent structures. They're both made of the same atoms, but they have different properties, and it's all due to the bonding. So in graphite, each carbon is bonded to 3 others. That means that we have a spare outer shell electron. So rather than sitting on the shell and making this system reactive, what it does is it sort of flies off. And if you think this carbon's bonded to another 2, that carbon's bonded to another 2, that carbon's bonded to another 2, and so on, we get this sort of sea of free electrons that can move and weave their way between all the little gaps. With graphite, we don't get a tetrahedral shape, so we'll get a layer of something called graphene, which is all these carbon things linked together. And then we'll get another layer of graphene. And they'll be slightly gapped, they won't be complete, and in the middle we'll have our sea of free electrons. So in between my hands, there's this sea of free electrons that are free to move around. Now, as we looked at with the hydrogen, we have these weak intermolecular forces. They don't require much energy to break, so quite often what happens is the layers are free and they can move and slide over each other. They're not stuck together because they're not covalently bonded. This sheet is covalently bonded, this sheet is covalently bonded. They're not. So they are free to move away and apart from each other. So if it was like this, they'd be free to move around because they're actually hovering, they're not touching. Again, each layer is called graphene. Collectively, it's called graphite. Again, just Google a diagram, just put graphite structure. You only have to recognise it. Again, you are not expected to be able to draw it. So let's look at the similar or the opposing properties for graphite. Diamond was hard and strong. Graphite is soft or brittle. So remember, the graphite is the exception to the rule. Graphite is the one that breaks all of the giant covalent structure rules. So soft or brittle, the layers can slide over each other and break off. High melting points and boiling points, that's because we've got lots of strong covalent bonds which require lots of energy to overcome. Identical to diamond, identical to every single giant covalent. They can conduct electricity. Yet again, this breaks the rules. That's because they've got these free or delocalised electrons that can move and carry charge. So in between the layers, the electrons are free to move and carry charge. In an exam, quite often you will get a question and it will be about a giant covalent structure. I've seen questions in the past that have asked someone to compare the properties of sodium chloride and graphite, for example. Or sometimes I've seen exam questions where they've been asked to compare graphite and diamond. The big tips and the exam tips that I would give you on these structures, first of all, look as to whether it is ionic, so is it a metal and a non-metal, or is it covalent? If it's got a single name, so for example graphite diamond, that means it's giant covalent. Okay, so just bear that in mind. If it's ionic, it will always be named as the metal and the non-metal. It doesn't have any of these sort of code names that are code for something. So it could be that if you look at it and it's sodium chloride and graphite, you'd go, right, sodium chloride is a giant ionic structure. That means it has this, this, and this. Graphite is a covalent structure, so it has this, this, and this. The other thing that always gets asked is it always asks you to state a property and explain the property. And what normally happens is people list the properties and think, brilliant, I've got my marks. And what they've forgotten to do is explain it. So if you ever have to explain them, or if you get a question like that, they're normally worth 4 marks. So you would say 1 property and its explanation, another property and its explanation. You'll see that I've used repeating phrases. So for example, layers that can slide. That's really important. Layers, 1 mark, that can slide, 2 marks. Lots of strong, 1 mark, covalent bonds, which require lots of energy to overcome, 2 marks. Free electrons, that can move and carry charge. You'll see that I've put that as well. If you just put free electrons, that would be worth 1 mark. If you say free electrons that can move and carry charge, that would be worth 2 marks. So everything I've written is worth 2 marks when I've put them on the explanations. So make sure that you sort of familiarise yourself with those things. It's a bit like when I've said strong electrostatic attraction, weak intermolecular forces, strong covalent bonds. If you get into the habit of writing those words together in an exam, you'll pick up marks and it'll just give you that reminder as to which is which. If you remember as well, just giant covalent structures, they go by the general rules. Graphite is the exception. So unless you see the word graphite, go with the general rules for them. So your task for today is just going to be some quick check questions because I'm aware that there's quite a lot of information here. You are going to have to go and have a quick look at the structure. You don't have to draw it, but I'm aware you've probably had to pause the video to make notes and things like that. So quick task today and then you'll get new stuff next week. Any problems, as per usual, just email your teachers and I'll speak to you all next week. Bye.